Assalamu alaikum. Welcome you all to another lecture on electrical machines. In the last class, we discussed about an ideal transformer and we discussed some of the magnetic aspects and saw that for an ideal transformer, the turn ratio is V1 or V2 is equal to N1 or N2 is equal to I2 over I1. In the today's class, we will continue our discussion on the transformers, but for this time we will discuss the real transformer. So let us start with the today's lecture. So let us draw a real transformer. Let us say that we have this core, and in this core we have number of turns Np on this primary side, and there are some turns on the secondary side, that we say this is Ns. Let us say we apply a voltage Vpt here. As a result, we have some current Ip T flowing into this particular transformer. Now, in a particular transformer, we do know that the induced EMF E induced is equal to d lambda by dt. So, this lambda is nothing but that is equal to sum of the flux passing through each coil of a given winding. So, that is equal to I equal to 1 till n, and that is equal to phi I. Now, as you can see here, for a given transformer core, we may have the flux. We may have the flux here as well as here and here. So, what amount of flux is actually linked with the windings on the primary side and on the secondary side? In order to have a simplified version, we take the average flux which is linked with these number of coils here, or with these number of turns here. So, for that, we say that this average flux phi is equal to lambda divided by n, where lambda is the flux linkage and n stands for the number of coils. So, this means that this lambda equals to n times the average flux given in this particular core. So, if we substitute this back into here, then this E induced becomes equal to n d average d phi over dt. Now, if we solve for this particular expression, if we solve for this particular expression for this particular flux, then that is equal to 1 over n integral v t dt. So, this particular equation, if we apply some voltage on this primary side, then this becomes equal to 1 over np integral vp t into dt. So, this average flux in the primary winding is proportional to the integral of the Vpt, and the constant of proportionality is this 1 over Np. Now, the question here is that if we have an unloaded secondary winding just like we have shown here, then how this particular average flux links with the secondary winding. So, for that, let us see what happens when we energize this particular primary winding of this particular transformer. So, as a result, what happened here is that we have some flux which is mutually linked with the core as well as on the secondary winding, and we call this one as phi m, which is the mutual flux. However, because of the non-ideality of this particular core, we have some of the flux which is not linked with the core or with the secondary winding. Rather, that particular flux is found outside in the air in this direction. So, the direction of this flux can also be calculated by using the right hand rule. So, you can see here that this particular flux, which is neither linked with the core nor with the secondary winding, is actually known as the leakage flux. It is known as the leakage flux, and we represent it as phi Lp here. So, from this particular expression, we come to know that if we have a real transformer, then not all the flux links with the secondary winding and the core. Rather, some of the flux remains in the air. It completes its path through the air, and therefore that flux is of no use, and hence we call it a leakage flux. So, here in this particular expression, we can see that this phi p, which is the average flux produced in the primary side, it has two components. The first component is the mutual flux, which is a useful flux, and the second one is the is the leakage flux, which is this Lk, which is this Lp, where P stands for the primary winding and L stands for the leakage which happens here. Now you see that this discussion is also valid if something is fed into the transformer from the other side. So we can also say that this average flux on the secondary side is also equal to the mutual flux plus the leakage on the secondary side, right? So based on this, we can rewrite the Faraday's law of Faraday's law as, so let me write the Faraday's law. So we have Vpt equals to Np d phi p by dt, and because this phi p has two components, so that becomes equal to Np d phi m over dt plus Np d phi Lp over dt, right? And on the similar grounds, we can say that the Vst equals to an S d average flux in the secondary winding d phi s over dt, and that is equal to n s d phi m over dt plus n s d phi l s divided by this dt. Now if we closely examine this particular expression, then we can say that this one is the EPT, which is the induced EMF in the primary side, and whereas this one is the ELP, which is the induced EMF due to the leakage flux in the primary winding. And similarly, we can also say that this part which is which contains the portion of the mutual flux, it is the EST, while this represents the ELS of the T, which is the leakage flux due to the secondary winding. Now we can see that this EPT, because this ELPT is of no use, it is a waste, and therefore it is of no use for transformer analysis. So we can say that this EPT is equal to Np d phi m over dt, and this EST is equal to Ns d phi m over dt. Now based on these two equations, we can say that T divided by Np, that is equal to d phi m over dt, and this is also equal to EST divided by this Ns, and therefore we can say that this EPT divided by EST is equal to Np over Ns, and that is the turn ratio in a practical transformer. So you can see that the voltage induced in the primary winding, the voltage induced in the primary winding and its ratio of the voltage which is induced in the secondary winding is dependent on the turn ratio of the transformer, which is the N1 over N2, or this is the Np over Ns. Now in a practical transformer, we ensure that this phi m is greater than the leakage flux on the primary side. So what we mean here, that we want to have this mutual flux as large as possible compared to the leakage flux in a transformer. So there are several measures that are adopted in order to enhance the mutual flux, or in order to keep the flux inside the core so that it can link with the secondary winding. There are a lot of measures. Some of them we have already studied, that is, we interleave the winding, and sometimes we use E-type core or a shell type core for a transformer, so that the maximum flux is linked with the windings which are wrapped on the limbs of a transformer. So similarly, based on this thing, we can say that if we manage to have this mutual flux greater than this leakage flux, then we can say that the Vpt over Vst is equal to Np over Ns. But if this thing is not valid, or if we fail to acknowledge this thing, then this equation is not satisfied. So next thing that we need to see is the magnetization current of a transformer. Magnetization current of a transformer. So suppose that we have this transformer here, and we have some applied voltage here, that is VPT. Now we want to see what happens if we do not connect any load with the transformer. So this is an open circuit. So here we have this VST. Now because we do know that this in a transformer, this VP over Vs is equal to NP over Ns is equal to Is over Ip. Now because this Is equals to 0, because it's an open circuit condition, in an open circuit we have that is equal to 0. So we should expect to have no current flowing into the primary side. However, this is not true. This is not true because there is some amount of current which is required to establish the flux in this particular core, and that current is known as the magnetization current of a transformer. For this particular transformer, suppose that we have, this is the NP and this is Ns. Again, we have as you can see that there is no load connected on the secondary side. Therefore, we expect to have no current flowing into the primary side. However, we want to have some flux established in this particular transformer so that we have the voltage available on the secondary side. So for that, a current flows from the primary side and it produces the flux in the particular core. But in a real transformer, it is not only the flux which is produced by this current IPT, rather we have the hysteresis and the eddy current losses as well that emerges because of the flow of this particular current. So we can say that the input current which flows through the transformer when there is no load connected at the output side, it has two components. So the first component is the IM, which is the magnetization current, and the second one is IH plus E, which are the hysteresis and the eddy current losses. And these losses also happen because of the flow of current. So there is something which is producing these losses, and therefore the sum of these two is known as the IX, or the excitation current of a transformer. Excitation current is drawn by a transformer whenever we connect some excitation source to a particular transformer and its secondary is kept open. So since we can see here that the average flux phi p, as you can see here, this average flux phi p is equal to 1 over NP integral Vpt into dt. So therefore, if we say that we have phi p equals to 1 over NP Vpt dt, then, and we also say that this Vpt is equal to Vm cosine of omega t, then the flux phi p becomes equal to Vm sine omega t divided by omega Np, and this will be in terms of in Webers, right, because this is the flux, so it will come in Webers. So we can see that if we plot these two values, then we have, if this is the applied voltage Vpt, then we have this is the flux phi p in a given transformer. So we can see here that that this particular section, if this is V and this is phi, because we have a 90-degree phase difference between these two, then this is the core losses current, and here is the magnetization current, and their vectorial sum provides us the information about this particular current, which is the Ix, and this theta, which is between this applied voltage V and the current which is drawn by the transformer at no load condition, this theta is known as the no load power factor of a transformer, and it is very poor, typically between 0.02 to 0.3. This is a typical power factor of an unloaded transformer. So let us see what happens if what happens with the magnetization current, and what is the shape of the magnetization current. So suppose that we have a material which has a very thin which has a very thin BH curve here, right? So it saturates here, and it passes through somewhere from this particular point. That this BH curve has some part which is sort of a linear part, and then we have a part which is the saturation part, or where the core becomes saturated. So one should notice that near this saturation point, that is in all this particular area where we have the saturation, a small increment in the flux requires very large amount of current, and therefore if I plot the magnetization current here, which is this IM, then till this particular point we have a current which increases like this, and when we reach this particular point it increases like this one, and it goes like this, and thereafter it also have some sort of a current like that, right? So this is the shape of the magnetization current which flows through the transformer when it is unloaded. Now this particular IM, it contains harmonics. This IM contains harmonics, and it is not sinusoidal, right? So you can see here that we have some distortion here, particularly in this particular area and in this particular area. So however, the good thing here is that this is actually a symmetrical, such that we have I naught t plus pi is equal to minus I naught into t, such that this is actually a symmetrical signal. This is symmetrical, right? So this is for the transformer with no load condition. What if we have a transformer? Let us say again we have a transformer here, right, and we have a few windings here, and this time we have some load which is connected here, right? So now let us say that we have, this is VPT, and this is VST, we have this IST, and here we have this IPT. So this is that dot convention as we have seen here. So now you can see that for this particular transformer, the current entering the dot end will produce a positive magnetomotive force F, right? So the current into the dot end produces a positive magnetomotive force, which we can actually show something like this one, right? This is F. And if the current leaves this dot end, it produces a negative magnetomotive force. So the total magnetomotive force in a given core only becomes equal to 0 if we have the current flowing from one dot end and leaving from the other dot end, right? So the net MMF in the core, which is this F net, that is equal to NPIP minus NSIS, and that is equal to the net flux in the core, which is this one. This is the net flux, not the average flux, rather the net flux in the core, and this R is the reluctance of the core, or the resistance in the core. So in magnetic circuits, we do not have the resistance, we have the concept of reluctance. While in electrical circuits, we use the term resistance to show that there is something which is resisting the flow of current. So in magnetic circuits, there is a concept of reluctance. So this F net, which is the net magnetomotive force, that is equal to the net flux in the core times the reluctance in a given core. So for a well-designed transformer, this reluctance R can neglect it. So it is approximately equal to 0. So you can see here that this F net is equal to NPIP minus NSIS, that is equal to 0. And therefore, based on this particular expression, we can say that is NP over NS is equal to IS over IP, and that is equal to 1 over A. These are all the approximated symbols, right? So this way, this is the reason we have the MMF equal to 0, and for that we say that in a dot convention, the current leaves one end of a winding, dot end of the winding, if the current enters from the other dot end of the winding. Suppose that we have an original flux produced by this VPT, and which is shown with this red line. So this is the original flux. Let us say this is phi 1, right? And we have, because of this phi 1, we have some induced EMF EPT along the primary side. Similarly, this EPT results in the secondary voltage. When it links with the secondary winding NS, it produces a voltage which is said to be equal to VST. Now when this VST is connected with some load, then we have some current which flows from this non-dot end and supplies this particular load. Now because we have a flow of current in the secondary winding as well, so this secondary winding will develop its own flux which will try to oppose the original flux, and because its direction is on the opposite side. So we have the original flux flowing in a clockwise way, whereas we have the counter flux produced in an anti-clockwise way. Now if you consider this particular thing, then you can see here that this part, only this part, I can model it something like this one, that we have a voltage source here, then we have the EPT here, right? And this current I is equal to VPT, which is this one, minus EPT divided by the impedance offered by this primary coil. Now as we have this counter flux generated by this IST, it will weaken this original flux. When this original flux will weak, then this EPT will reduce, thus this I shoots whenever we have a counter EMF produced in the coil, and thereby it balances out this flux which is produced by the flow of the secondary current, right? So this is one thing that we should notice, that the amount of flux which is reduced by the load current or by the flux produced in the secondary winding is compensated by the increase in the current from the input side IPT, such that the things actually balance out the effect. So till now we have seen the ideal transformer as well as the practical transformer. So let us summarize the ideal transformer as well as the non-ideal transformer. So in an ideal transformer we have mu equals to infinity. So the BH curve is vertical, right? So we have this BH curve. BH curve is vertical because this mu, which is the permeability, is equal to infinity. Also we have this B saturation is equals to infinity. So the core never saturates in an ideal transformer. Whatever is the applied voltage, whatever is the applied frequency, the core always works, and therefore there is no concept of the saturation in an ideal transformer. And then we have the resistance offered by the resistance of coil or the winding equals to 0, and so we have 0 losses in the winding. Also we have the resistance of core equals to infinity, so there is no eddy current losses in the core. Whereas for a practical transformer, we mu is not equal to infinity, rather it has some finite value which depends on the material which is selected for a given transformer design. Also we have this B saturation, it is not equal to infinity, it saturates at some particular point. Then this coil winding is not equal to 0, and so is the resistance of the core, which is not equal to infinity. So now that we have studied the ideal transformer and the real transformer, let us model a transformer in terms of its equivalent circuit, such that we can use the linear circuit elements like resistance and inductance to replicate or to model a transformer, to model a practical transformer. So this particular topic is known as the equivalent circuit of a transformer, right? So we have seen that if this represents an ideal transformer, then we should add losses in this particular scheme so that it represents a practical transformer or a real transformer. So what are the type of losses which can be incorporated into this ideal transformer model? So for that we can add, first of all, the losses that can be added are the copper losses, because copper is used usually to have the number of turns on the primary winding and number of turns on the secondary winding. So the first thing we can encounter is the copper losses. That is, we want to have the I square R losses into the particular system. Now because we are winding the number of turns on a primary side as well as on a secondary side, and we are not using a superconductor, something which is the lossless material, therefore that can be incorporated by adding a resistance in the primary side as well as on the secondary side. So the model of a transformer after incorporating these copper losses becomes something like this one. So we have a winding resistance which is Rp for the primary side, and then we have this resistance Rs which is on the secondary side. Now these winding losses are the current losses, and they are modeled by using this resistance Rs and Rp, and they are dissipated in the form of the heat. So what is the other part associated with the primary winding and the secondary winding? Now because we have earlier seen, not all the flux produced due to the current flow in the primary winding is linked with the secondary winding or the core. We do have some leakage available. So how can we model that leakage in a given transformer? So for that we have to dig a little bit into the magnetic concept. So we do know that the leakage inductance ELP is equal to NP d phi LP over dt. This is the leakage due to the primary side, and similarly we have leakage due to the secondary side as well, where this is NS d phi LS over dt. Now we also know that the reluctance in air is very much greater than the reluctance in the core, because core is a material which is designed specifically for the magnetic field lines, whereas air has a very high reluctance. So therefore we can say that the resistance in the air is very much greater than the resistance in the core. So this means that this phi LP is equal to NP over, which is this R represents the reluctance, and this IP is the current which is flowing here. So this reluctance actually defines how much of the flux is actually leaked from the core. So this R, which is the reluctance, can be written as this NP IP into this thing. This is known as this particular thing is known as the permeance, and this is nothing but it is the same concept as that of a conductance in an electrical domain. So in an electrical domain we have the resistance R, and that is equal to 1 over G, where G is the conductance, right? This is the conductance. In magnetics path we have we have this R which represents the reluctance, whereas we have this one P which is the permeance or the conductance in a given magnetic field. So based on this particular thing, we can say that this phi LP is equal to this one, and phi LS is equal to NSIS into this permeance P, right? So if I substitute this one in here and this particular thing in here, then we have this ELP T is equal to NP d by dt into permeance into NP into IP. So that is equal to NP square into permeance into dIP over dt. And similarly, this ELST becomes equal to NS square, this permeance into DIS over dt. So now if we look onto the definition of an inductor, suppose that we have an inductor here which is linked with its own flux, right, which is linked with its own flux, and we have some current I flowing here with some applied voltage V here. Then if the flux path, which is this particular path, it has a constant permeability, right, then the flux linkage phi and current are said to be linear, right? So we, in a linear inductance, we have this flux linkage lambda and this current I, they have a constant permeability, and therefore this is known as the inductance L. So this L is equal to lambda over I, and that is equal to N phi over I, and that is equal to N square over R, or the reluctance, or which is equal to N square into the permeance. So this concept can be retrofitted here, and therefore this ELP, which is a leakage flux in the primary winding, is equal to LP dIP over dt, and similarly ELST is equal to LS DIS over dt. So this means that the leakage flux in the primary winding or in the secondary winding can be modeled by using an inductance L. So if we incorporate this particular concept in the equivalent model, then the equivalent model, which was previously only having the resistance RP here, we have this equals to JXP here with the transformer windings on the secondary side as well. So we have this was RS, and this is equal to JXS on this particular side. So here we have this VS, this is IS, this is IP, and here we have this equals to VP. Now the third thing here is that we have actually incorporated the losses in the windings. What about the core losses? So to model the core losses, we need to establish that the core loss is of two types, right? The number one is the current which is required to produce the hysteresis and the eddy current losses, and the other one is the magnetization current LM, right? Magnetization current IM. What is this magnetization current? This magnetization current is actually that current which is required to establish the flux in the core of a given transformer. So we have seen that the magnetization current IM is actually lagging the applied voltage, and therefore it can be modeled in terms of an inductance. So IM can be modeled in terms of the inductance LM, whereas this IH plus E they are heating losses, and therefore we can model it by using a resistance R, right? So but this comes in parallel with the with this particular winding. It will not come in series because it has nothing to do with this particular winding. Rather, it is something which deals with the losses in a given core. So the equivalent circuit is something like this one. So this is RP, we have this JXP, and then we have this is RC, which is the core losses, and this is the JXM, which is the magnetization branch, and we have this is the VS VPT, and here we have the IP and this T, and on the other side we have this is the number of windings, and here we have the RS as well as the JXS. This is the voltage VST, and here we have the current IST, right? So this is the so-called exact model of a given transformer. Why we are saying that this is a so-called exact model of a given transformer? Because the effect of capacitances is ignored. So we call it so-called exact model of a transformer. So-called exact model of a transformer, right? Now, as you can see here, we have this number of turns NP here, and we have number of turns NS here. One way of further simplifying the circuit is to bring all these secondary elements onto the primary side. And in an earlier lecture, we have seen that if we want to transform these resistances onto this primary side, then they are multiplied by a square. Whereas this voltage and the current goes with the typical expression of a transformer, which is V1 over V2 is equal to N1 over N2 is equal to I2 over I1. So if we bring these onto this particular primary side, then we have the equivalent circuit is that we have this is equal to RP, this is JXP, and here we have the RC, and then we have this JXM, and on this side we have this RS A square into RS, and here we have J A square into XS, and here we have the voltage VPT, this is the voltage IPT, this is the current IST over A, and here we have the VST into A, or that is also equal to A into VS. If you see here, this equivalent circuit has an additional node here. If we do not have this additional node, then we may actually add the resistances in series and the inductances in series. So one way of having an approximation is, so we shift this particular branch, which is known as the excitation branch, onto the extreme left side, right? So if we can do this, then we can actually add this particular RP and GXM with this A square RS and J into A square XX. But to do so, we can only do this by stating that this excitation branch current is only this current IX, right? This IX is usually 2 to 3% of the full load current, right? And therefore, if we assume that this current is negligible, then we can shift this onto this particular side, thereby allowing us to add these components such that they are connected in series. So there are certain equivalent circuits which are known as an approximate circuits here. So let us write this as approximate equivalent circuits of a transformer. So we have the excitation branch here, and right after that we have an R equivalent, and we have the JX equivalent here, right? So if the circuit is referred on the primary side, then this is VP and this is IP, RC, JXM. Then we have this equals to A times VS, and here we have IS over A, right? So if it is referred to the primary side of a transformer, then this R equivalent is equal to RP plus A square into RS, and this X equivalent is equal to XP plus A square into XS, right? So if this transformer, if it is referred to the secondary side, secondary side, then we have this RC is divided by A square, Also we have JXM divided by A square, and similarly this R equivalent becomes equal to RS plus RP over A square, and we have this X equivalent equals to XS plus XP divided by A square. We also need to modify this particular thing where this will turn out to be equal to VP over A, and this turn out to be equal to A into I into IP. So everything has to be shifted in a uniform way if we are referring the primary side to the secondary side or the secondary side to the primary side. We can further simplify this approximate model by neglecting this excitation branch from this T circuit. Remember that this original circuit is also known as the T model of a transformer, right? So this is an exact model of a transformer. So we created an approximate equivalent circuit of a transformer by considering that this excitation branch can be moved from this middle point to this particular point. We can further simplify this given circuit based on the amount of, or based on the application and amount of the accuracy which is required for the analysis of a transformer. We can actually neglect the excitation branch from a transformer, because most of the people might say that this is just 2 to 3% of the full load rated current, and therefore we can actually neglect the this excitation branch altogether from this particular model. And if we do so, then we are left with only this simple circuit, which is this R equivalent and which is this JX equivalent. So if this is VP and this is IP, then we have this one IS over A, and this is equal to A times the VS. So this is the extremely simple model, simplified model of a transformer, right? Now we have the question is now that we have obtained an electrical model of a transformer which actually replicates the losses in a given transformer and which tells us about the performance of a given transformer. The point here is that unless and until we have the information about the values of this RP, RS, JXP and the JXX and this RC and JXM, we cannot actually use it to find out what is the efficiency in a given transformer. At what load condition, we cannot find it out. So for that, there are certain tests in a transformer which are performed. So let us see what are these. So these are typically two tests. The first test is known as the open circuit test, right? So in an open circuit test, we have, for example, we have this transformer, right? And in this transformer we have, this is NP and this is NS, right? And one of the winding is left open circuit, right? One of the winding is left open circuit. So which winding is left open circuit, and on which winding we take the measurement? This is the first question. So but first of all, let us excite this through some voltage source Vt. I am also measuring the voltage V here, the current in ampere, and also through a wattmeter I am measuring the power here. So this is the wattmeter here, right? This side it is left open circuit, and hence this test is said to be is known as an open circuit test, or this test is called an open circuit test. Now we are having this wattmeter here. This series branch of this wattmeter is used to measure the current, while as this shunt branch is used to measure the voltage in a given wattmeter. Also we are measuring this A. Let us call this one IOC, because this is the current which we are measuring in an open circuit test. So in order to differentiate it with the other test that we will discuss shortly, we designate this as an IOC. Similarly, this is equal to VOC. Now we have a question that what winding or what part of a transformer is left open circuit while we perform this particular open circuit test. Now that depends entirely on the ratio. For example, we usually perform it on the low voltage side, right? So the first thing here is the winding which is open circuit is usually the one with high voltage, which means that all the measurements are made on low voltage side, right? Because it is easy to handle the low voltage. So, for example, if we have for a transformer, if we have a transformer rating something like this 8000 over 240 volt, this means that we need to open circuit the winding which is designed for this 8000 volt. So we do know that this A is equal to Vp over Vs, and that is equal to 8000 over 240. So we will select that the primary winding Np is open circuited, and this Ns is used to measure the voltage, current, and the power, right? So what we are actually trying to establish here, that with the open circuited winding on one of the windings, which is of course the high voltage winding, we open circuit that particular winding. So what we get left is actually a transformer where we are only providing the excitation current, right? So based on this particular thing, since we know that only the excitation branch is drawing the current, so the equivalent model of an open circuit test is something like this one. So we have this Rs, this is Jx, sorry, this is Rp, this is Jxp, just to simplify this one, and here we have this Rc, and here we have this Jxm, and here we have this particular transformer, and here this transformer winding is an open circuit winding, right? So since I am measuring the current here A, so whatever is the current here, it goes through this particular branch, which is the excitation branch. Now we do know that this Rc is a very large value compared to this primary side resistance Rp, and therefore I can say that whatever is the current flowing here, which is designated as IOC, it is actually the current which is the same current that is flowing through this particular branch. Also we have this Xm greater than this Xp. Now based on this particular assumption, we say that all the current flows through one side of a transformer, and most of the voltage drop occurs along the excitation branch, right? Because it's a series circuit now, so this current, which is this one, let us say this is IOC, it is actually having a producing some voltage drop across this impedance as well as across this particular branch, which is the excitation branch. Now because this excitation branch has a value which is very much greater than these series branch elements, and therefore the majority of the voltage drop across this particular excitation branch. So because this is negligible, so we can actually say that this circuit is left out when we undergo an open circuit test in a given transformer. So here we have the applied voltage, this is Rc and this is Jxm. To further simplify this particular test or the results, what we do, we take 1 over Rc, that is the conductance, and we also take it equal to 1 over Bm here. Now because these taking down the opposite or the inverse of this Xm and this Rc, we have 1 over Rc equal to Gc, and this Bm is equal to 1 over Xm. So taking on with this thing, this Gc, which is the conductance of this Rc, that is equal to 1 over Rc, and this Bm is equal to, which is the susceptance, equals to the 1 over 1 over xm. So the total impedance or the total admittance of this circuit YE, total admittance which is YE, is nothing but that is equal to GC plus JBM, right? This is equal to JBM. So now this YE is also equals to the IOC over VOC, and that is why we are measuring the voltage here as well as the current in this particular circuit. And alongside we are also having a wattmeter which gives us the power rating, or which is known as the POC here. So the power factor here is equal to cosine theta, that is equal to POC divided by VOC into this IOC. So this theta is equal to cosine inverse of POC divided by VOC into this IOC. So this YE is equal to IOC divided by this VOC into minus theta, right? So based on this particular thing, we get that the 1 over RC plus J1 over XM, that is equal to IOC over VOC at an angle of minus theta. So because this is actually a polar coordinate form, so once we get some value, polar is converted into rectangular form, right? And that is equal to A plus, let us say A plus JB. So whatever is this A, it is equal to the value of the core resistance RC, or which represents the losses in a core, and whatever is this B, it represents the impedance, it represents the magnetization branch of a transformer. So this RC equals to 1 over A, and this XM equals to 1 over B. So this particular test, which is known as an open circuit test, it provides us the information about the excitation branch of a given transformer, right? So now that in a transformer test, we have the information about this RC as well as this JXM. So what is left? We are left with these elements, which is the RP, XP, and RS and XS. To find out that thing, we develop a scheme which is known as a short circuit test, right? Now short circuit test is always performed that particular winding which has high voltage and low current. So the scheme is quite simple. Again, we have a variable AC supply, we have the voltage here, voltmeter, we have the ammeter here. Here we have the wattmeter. This is again, this is the wattmeter. Then we have a winding here, and this winding is usually the low current winding, right? And we have a short circuit here. This is short circuit, right? So in this previous example, as you can see here, for a 20 kVA set, if this VP is 8000, then it has low current, and therefore it will now be performed on the primary side if we consider this particular example of 8000 over 240. So in here we have the secondary, which is low voltage, high current side, and this side where we perform this test, it is high voltage, low current side, because low currents are easy to manage. So now we have this voltage which is equal to VSC, this A is this ISC, and we have this wattmeter which gives us the power, which is PSC here. Now we slowly increase this VT here, VT is varied, we slowly increase it from 0 such that the ISC becomes equal to the rated current of this particular winding over which we are taking the measurements, right? So when it becomes equal to this rated current, we fix this VT here and we measure what is this VSC and what is this ISC and what is this PSC. Now once we do that, we have a rated current available here, and we have earlier seen here that this excitation branch is 2.2 to 3% of the full load current, right? This means that this current which is flowing here, majority of that 97% of the current flows through the windings of the transformer. So therefore the equivalent circuit of according to this particular transformer test is something like this one. So we have R equivalent and we have this JX equivalent here, right? So this is the applied voltage VT here. So we can say that that this current, which is this ISC, it represents the current which is flowing through the windings of the transformer, and therefore by having the values of this voltage VSC, this current ISC, and this wattmeter rating PSC, we can actually establish what is the amount of the resistance and this JX equivalent. So for that we do know that ZSE is equal to VSC over the ISC, which comes from the short circuit test. Also we have power factor that is equal to cosine theta, that is equal to PSC divided by the current and the voltage measured through this voltmeter and the ammeter, and therefore this theta is equal to cosine inverse of this PSC divided by VSC into ISC. So with this thing in mind, this ZSE is equal to VSC over ISC into at an angle of theta. So this is also equal to the R equivalent plus JX equivalent, right? So this is in polar form, this is in the rectangular form. So this is polar and this is the rectangular form. So once we obtain this particular value, we can convert this polar into rectangular form, and the real part will give us the R equivalent and the complex part give us the X equivalent. Remember that these are the equivalent values. It is not a trivial thing to find out what is the value of the RP and what is the value of this RS, right? So it gives you a collective resistance offered by both the windings on the primary side as well as on the secondary side. Now another alternate method of finding this R equivalent is to divide this power PSC divided by the square of the current measured through that particular ammeter, and thereafter we can have this X equivalent equals to the Z equivalent square minus the R equivalent square, right? So this gives you this X equivalent here. So all side, and once you get these particular values, because you can see that for a given transformer example that we have said, this is 8240. So one test is performed on the secondary side, one test is performed on the primary side. So before you model a complete transformer, before you model this particular, for example, here we have this is our model. So you have to completely take it on one side. So if it is referred to on the primary side, then you have to refer this particular side, or this particular, or whatever the side which is measured on the secondary side, you have to refer it to the primary side to get the original values here. So we stop here, and in the next class we will inshallah cover some examples of the transformers, and thereafter we will move on to the further topics. So if you have some questions, you can leave them in the comment section so that others can also read. So till the next lecture, take care and Allah Hafiz.